Space, time, life itself. The secrets of the cosmos lie through the wormhole. In a way, every man, woman, and child on this earth is a time traveler. Like it or not, we're all being shot relentlessly forward, making the journey from birth to death, and there's no going back. And there is no way of looking into the future. Or is there? What if we could travel back to witness events in the distant past? Or journey into the far future, see our destiny? Just think what we might learn if we could watch history unfold right before our eyes. Or what we could change in our own lives if we had the chance. For many, life's greatest sorrow is losing a loved one. The time I spent with my grandmother when I was a child helped make me the man I am today. I often wish I could see my grandmother again, or go back in time and show her who I am and what I've become as an adult. Seems like an impossible dream. But is it? Can science find a way to tear down the walls between now and then? Is time travel possible? To find the answer, we must first understand the nature of time. And that's a lot harder than it sounds. Steve Jeffords is an atomic scientist and master timekeeper.
We all, I think, have some innate feeling that we understand time. It flows past us. Time goes on. We get older. Things that happened yesterday are not happening today, etc. But I don't think that any of us, whether we're physicists who study time or just somebody who lives his life, really truly understands time.
Steve works at the National Institute of Standards and Technology in Boulder, Colorado. It's one of 6 labs around the world that calculate coordinated universal time, the official world time. This table full of lasers is the NIST F1 cesium fountain atomic clock. Measuring the nuclear vibrations of atoms, this clock ticks at 9 billion times per second. That's 1/10,000,000th of a nanosecond.
This clock will measure frequency or time interval out to almost 16 digits. Why is that important? The reasons to measure time or frequency this accurately, boy, there are a bunch of them. Some of them are scientific, but some of them are really practical. Systems like the Global Positioning System, the GPS system, it's fundamentally a timekeeping system. And so what we do is we put atomic clocks on satellites, make sure they're all synchronized, and now I stand on the surface of the Earth with my GPS receiver, and it gets time signals from each of these satellites, and it just measures the arrival times. And so if the signal from that satellite arrives 5 nanoseconds before the signal from that satellite, it says, oh, I must be 5 feet further from that satellite than that satellite. So it does that with 4 satellites, and it computes your X and Y position and your altitude, and now you've got your position from time. And the fact that this works at all is just remarkable, but it absolutely depends on having time at the nanosecond level. Because if you don't have time at the nanosecond level, then you can't tell which satellite you're closer to.
Precision timekeeping like this makes our high-tech computer-driven lifestyles possible. But as our timekeeping systems become ever more accurate, we find that time does not flow the way we think it does. Time is not universal. The strange truth is that time is personal. What time is it? Well, that depends on where you are and what the ground beneath your feet is doing.
Anytime you put a clock in a gravitational field, as you get closer to the strong part of the gravitational field, the clock slows down. What ends up happening is that the Earth is not rigid. And the Earth is sort of a squishy, firm ball of jello or something. And every day when the tides go in and out, the Earth deforms sort of like a ball, and the earth under your foot goes up and down by a foot, more or less. Depends on where on the earth you are. So if I pick this clock up and move it up by a foot, it's further from the center of the earth. The gravitational force goes down a little bit, and the clock ticks a little bit faster. So now if you have a clock which is accurate to 17 digits, all of a sudden, every day, you can see the rate of the clock speed up and slow down and speed up and slow down relative to what it should be, because the Earth is squishing by this kind of 1 foot level.
Humans don't perceive these minuscule time differences, but our very fastest clocks can cut a second into a quadrillion pieces. And at that scale, we see that time differs from place to place. Time and space are tightly locked together.
Quickly, we're getting to the point where we're going to have to start thinking about space-time together rather than space and time, which is, this is a cool thing, cool place to be, right?
Gravity slows time, and this is the key to one form of time travel. When you leave a gravity field such as the Earth's surface, time moves at a different rate for you than for your friends on Earth. The time difference is greatest when you move at high speed. This means that time travelers walk among us. These are their time machines. Cosmonaut Sergei Krikalev is the world's greatest time traveler. Krikalev has spent 803 days moving at 17,000 miles per hour. He traveled fast outside the Earth's gravity, so time moved more slowly for him than for us. Because time passed at different rates, he has traveled into the future, a 48th of a second into the future. A 48th of a second may not sound like much, but stick more power behind him and make him go faster, near light speed, about 670 million miles per hour, and things get strange. If he travels for a year, he'll come back and find out that while he has aged 12 months, Earth is 10 years older. Here is another time machine, and it speeds things up even faster than our rocket ships. It's Europe's Large Hadron Collider, or LHC, the world's biggest and baddest particle accelerator. Steve Nunn is a professor of physics at MIT. Using the LHC, Nunn and thousands of other scientists turn pieces of atoms into time travelers. They take protons, accelerate them to nearly the speed of light, then smash them together. The subatomic particles that come out of the explosions only live for about a billionth of a second. But in the LHC, that billionth of a second is stretched out relative to our time.
The LHC here at CERN is like a time machine because of a funny feature of physics. Velocity is not what you think it is. Velocity at normal speeds is normal, but at very, very high speeds, velocity has a maximum limit. So the protons in the ring are traveling near the speed of light, and they can't go faster. What happens instead is that their clocks start moving slower. Their ticks are longer than our ticks. So in some sense, the protons that are going around the ring, their clocks are moving slower than our clocks, so they're like time travelers relative to us.
The time-traveling protons at CERN show us that we, too, can travel far forward in time. Decades from now, spaceships traveling near the speed of light could fly into the stars on a 10-year mission. For the people on board, it would be 10 years. On Earth, 1,000 years would pass. the astronauts would return to a far different future world. Time travel into the future is possible. But is it a one-way trip? Can we make our dream of time travel backwards and forwards come true? With the right technology, time-traveling spaceships could take us into the future. But can we go against the arrow of time and journey into the past? Well, it may not be as hard as it sounds. I mean, after all, the past is all around us. Consider this. The speed of light is 186,000 miles per second. Now, that's awfully fast. But when a piece of light travels from here to there, it takes time. And that means that everywhere you look, you're looking back in time. It takes 1/1000th of a second for light to travel 1 foot. So you see the person you're sitting next to 1/1000th of a second in the past. The light from the sun is 8 minutes old when we see it. And the deeper we gaze into the sky, the farther we see back in time. Satellites have photographed the edge of the universe, 13.7 billion light years away. That's 13.7 billion years back in time. We always look into the past, but it goes even deeper than that. According to Einstein, time is just like space. Since every bit of space exists here right now, that means that every bit of time exists right here, right now, too. Sean Carroll is a physicist at the California Institute of Technology.
Physicists tend to be eternalists. They think that the whole universe, the whole four-dimensional space-time in which we live, is equally real. We exist at different moments in this space-time continuum, and we feel different things at different moments of time. But it's not that the future is becoming real as time goes on. It's just that the future exists just as much as the past or the present. We're discovering what happens in the future as time goes on. But it's not becoming any more real, and the past is becoming real. So we think that in principle, the past and the future exist just as much as the present.
The whole of time is all around us. But can we jump from the present to the past? In the early years of the 20th century, a young patent clerk named Albert Einstein gave us a possible way back. Riding to work on a streetcar, the barely 20-year-old Einstein looked up at a clock tower, and suddenly it all clicked. Einstein realized that time is relative to where you are and how fast you're moving. Time is the fourth dimension, bound tightly together with length, width, and depth, the dimensions of space. A few years later, Einstein used his ideas about gravity's effect on space and time to create a mathematical map of the cosmos. He proved that the fabric of space and time is curved. If the universe is curved, there might be ways to build bridges across it, or create loops inside of it, loops that will allow time travel. That was the conclusion reached in 1949 by the mathematical genius Kurt Gödel. Gödel was a close friend of Einstein's, and he decided to see if the great man's equations permitted time travel. He found that they did. If the universe rotates on its axis and you somehow remain perfectly still, it would be possible to go to any time and place in the universe. An exciting discovery, except that we now know that the universe does not rotate. And without the rotation, you cannot have time travel. Gödel's solution was unrealistic, but his radical thinking inspired a new generation of explorers. Professor Frank Tipler was one of the renegade physicists who followed in Gödel's footsteps.
I was fascinated by Gödel's paper, which I had actually read when I was an undergraduate at MIT, and I wondered if I could follow up Einstein's suggestion, can this be actually done physically? We can't rotate the universe, it either is rotating or not, but we might be able to do something on a smaller scale. And obvious, easy-to-solve model in relativity was a rotating cylinder. And so I was able to show that a rotating cylinder would give rise to these loops in time, being able to go backwards into time.
Tipler's gigantic cylinder would hang in space, whirling at nearly the speed of light. Space turns into time, and time into space as both become twisted around the cylinder. So by traveling forward around the cylinder, you go backwards in time.
Time direction is this way, but around a very rapidly rotating body, you can go backwards into a spiral like this and go backwards into time. So, my paper, which I tried to get published under the title of Constructing a Time Machine, the editors thought, well, that was a little too radical, and they wanted something that would not be so sound-bitey. And so I changed the title to Rotating Cylinders and the Possibility of Global Causality Violation. Now, there is a mouthful that no one will catch on to unless you actually read the paper.
But later, Tipler found there were a few problems with his idea.
I realized that the rotating cylinder, although an easy to construct solution to the Einstein equations, was not very realistic because it had to be an infinite cylinder, and creating an infinite cylinder is hard as creating a universe, which obviously we cannot do. So I was wondering if it would be possible to have this sort of structure in a much smaller scale, and I discovered, alas, that's not going to be possible, because if you tried to speed up a body to generate the time machine, what you would find before the time machine property was created, you would rip a hole in space and time. You would create a singularity right there in space and time. So, alas, I had to give up my dream of creating a time machine.
Tipler's spinning cylinder might not work, but there are massive objects in the universe that are already spinning near the speed of light. Black holes. The immense gravity of black holes push the laws of physics to the extremes. Could the secrets of backwards time travel lurk in their Stygian depths? I've got a lot of questions.
Through the Wormhole with Morgan Freeman, Monday at 9, all new on Discovery HD Showcase.
Black holes are small but incredibly massive objects scattered throughout the universe. The intense gravity of a black hole warps the fabric of time and space more than any other celestial object we know of. Can the time-warping properties of black holes be harnessed? Can we use them to travel through time?
Black holes are not time machines. You would fall into a singularity and you'd be crushed and you would die. Some interesting effect that we don't yet understand about what happens at the center of a black hole, there's no reason to think that it pushes you backward in time. The black hole is more or less a one-way street. You go in and you will never come back out.
So black holes won't work. But another cosmic anomaly made famous by science fiction might do the trick. Wormholes. Wormholes are magic doorways connecting two remote locations. These cosmic sky bridges would allow us to jump across space and travel in time. Fly into a wormhole and you can take a shortcut to another place or time. We have no proof that wormholes exist, but there is plenty of solid science behind them. No one knows more about wormholes than renowned physicist Kip Thorne. For starters, he can tell you why they're called wormholes.
If you have an apple, a worm drills a hole through the apple, reaches from one side to the other. You can think of the surface of the apple as being like our universe, and the worm has gone through some higher dimension to reach the other side.
If they exist, wormholes are smaller than atoms. If we want to go through them, we need to stretch them out and hold them open. Prying open a wormhole would take a tremendous amount of energy. Not just ordinary energy, but something called negative energy. Negative energy is anti-gravitational. It repels the fabric of space and time and would prevent gravity from crushing a wormhole. One problem: a lot of people don't believe negative energy exists.
Kind of energy that would anti-gravitate is ridiculous. But in fact, in modern physics, we know examples of negative energy that are created in the laboratory every day. Small amounts of negative energy, often just transient, but nevertheless negative energy. And so I was not willing to dismiss this possibility out of hand. The fundamental question was, could a very advanced civilization accumulate enough negative energy and hold it in the interior of the wormhole long enough to keep the wormhole open so that somebody could travel through it? The answer is we don't know.
Meanwhile, another renegade physicist worked up a different way to harness the time-warping effects of celestial phenomena. Richard Gott has been studying the problem of time travel for decades. Gott's novel Time Machine uses the heavy gravity surrounding cosmic strings to create loops in time. Cosmic strings are thin strands of energy that may run through the universe.
There's a poem. There was a young lady named Bright. She traveled far faster than light. She left one day in a relative way and returned home the previous night. The trouble is, Einstein also told you that you can't build a spaceship that goes faster than the speed of light. But in general relativity, which is theory of curved space-time, if you take a shortcut, you can beat a light beam. So this is what allows you to circle the cosmic strings and, like Miss Bright, visit an event in your own path.
And no one knows if cosmic strings are real. But many physicists think they're out there. Pieces of high-density vacuum energy left over from the Big Bang, narrower than an atomic nucleus. Some strings may be short, some may be infinitely long, but they all exert incredible gravity. And where there's incredible gravity, there's a chance of creating a shortcut across time and space.
So here's how to build a time machine using cosmic strings. Now, you might think that the geometry around a cosmic string is flat like a piece of pizza, but actually, because they have a large mass per unit length in the string, it really looks like a pizza with a slice missing. So if I cut out a slice of pizza here, take it away, and then I fold up the pizza so it's like a cone. Pizza looks like a cone. So if I was over here on planet A, I can send a light beam to planet B. But I could get on a spaceship and I could go slower than the speed of light and travel over here across this shortcut, and I can get there ahead of the light beam. Now what that means is that my departure and my arrival are separated by more distance in space than distance in time. In other words, this might be 4 light years in distance and only 3 years in time. So then what you could do is I can cut out another missing pizza slice here. And now I've got two cosmic strings, and then it's folded up like a boat. That's what space-time around the two cosmic strings looks like. So then what I can do is if I circle the two cosmic strings with my spaceship, I can arrive back to planet A at noon. Now, planet A at noon is the same time and the same place. So I can come back and shake hands with myself as I departed. So my older self can come back and I can see myself off. This is me visiting an event in my own past. That's real time travel to the past.
But, once again, there are one or two problems with this. For starters, when you push two cosmic strings together at high speed, it may create a black hole.
You may be killed after doing the time travel, or you could be killed before you even complete the time travel. The other thing is that this loop would weigh about maybe half the mass of our galaxy if you wanted to travel back in time a year. And so this is a project that only super civilizations could attempt. It's far beyond what we're able to do.
Physicists like God don't claim they can build working time machines today. They're trying to figure out whether the laws of physics permit time travel at all.
There are several inherent problems in all scenarios for building time machines, and that is that nature appears to have a driving force that may always cause a time machine to self-destruct at the moment you try to activate it. The answer as to whether you can get around it is held tightly in the grips, we believe, of the laws of quantum gravity, laws that we don't yet understand.
We know how gravity affects large objects like people, our planet, and the stars in the sky. We don't understand how it works deep down at the quantum level, the super small domain of waves and particles. But not understanding something has never stopped people from experimenting.
It seems that time travel is next to impossible in Einstein's world of space and time. But there's another world, and another kind of physics, where Einstein's rational rules don't always apply. It's the world deep inside the atom, where the weird laws of quantum mechanics take hold. Now, don't be scared. This is strange but fascinating stuff.
Quantum mechanics is just the idea that what exists is much richer than what you can observe. So when you look at a particle, you see it in one place. Quantum mechanics says that when you're not looking at it, that particle exists all over the place. Maybe it's more likely that you'll see it one place or another, but there's really a spectrum of possibilities for where you will see the particle. So when you combine the ideas of quantum mechanics with the ideas of time travel, all hell breaks loose.
One of the strangest properties of quantum mechanics is called non-locality. It's when two particles instantly affect each other, even when they're miles or light years apart. It's a bit like voodoo. When you stab the doll, the human being is also affected. But unlike voodoo, quantum non-locality is scientifically proven. Today, Swiss banks fund experiments to see if non-locality can be used to make one-of-a-kind, crack-proof security keys for computer transactions. Professor Nicolas Gissin leads the way. A quantum physicist and a fiber optic specialist, Gissin has tested quantum non-locality by showing the perfect synchronization of photons, particles of light, separated by great distances.
Quantum physics says, well, what happens is that whenever you do something on one photon, the reaction is not on this photon only, but there's a global reaction of two photons. In some sense, the two photons, although they are at this large distance, they still constitute one system. And so the global system reacts at once. And this is quantum non-locality.
Gisin sends photon signals through fiber optic cables stretched across Geneva. A pair of photons on one end is activated with a laser, and the photons on the other end instantly react. Nothing seems to move, and no energy is exchanged. Yet somehow, the particles share information.
Einstein used the word spooky action at a distance. So this spooky action at a distance is not something that travels in space-time. It's not something that happens in space-time. There is no story in space-time that can tell us how these non-local correlations happen. And that's why we conclude that they seem to emerge somehow from outside space-time. So that has, of course, deep implication for our understanding of space-time, or actually more precisely for our non-understanding of space-time.
Some believe that quantum non-locality can be used to send messages backward in time. At the University of Washington, physicist John Kramer is putting this idea to the test. Like Gisin, he's experimenting with entangled photons, photons bound by non-locality. The twist is that Kramer is trying to send photon signals from the present back to the very recent past. These custom-made lasers and measuring devices called interferometers are the heart of Kramer's time machine. One interferometer called Alice sends photon signals to another interferometer called Bob. If Kramer's theory is correct and the calibration is just right, Bob will get a message from Alice a fraction of a second before she sends it. Cause and effect will be reversed.
So Alice has control over whether we have particle-like behavior or wave-like behavior over here. Because the photons are entangled in space, Bob, who wants to receive the signal over here, can look and see whether he has an interference pattern at the same time. Now, this distance is a few centimeters. It's not very big, but it doesn't have to be a few centimeters. This could be a light year down the line, and she could still do the same thing and cause the same effect over here. And that's the way entanglement works. And so if I put a spool of fiber optics in here that's, say, 10 kilometers long, then she would send the signal 50 microseconds after Bob received it. So she would be sending messages backwards in time by 50 microseconds. So one could use it in principle for backwards in time communication.
If Kramer's device works, it will only send messages back a millionth of a second before they're sent. But a signal showing itself even a tiny bit in the past would revolutionize our understanding of time. It would prove that retrocausality, the theory that events in the future affect events in the past, is true.
If it does work, it would be quite remarkable. It would be a big deal in physics. It would be a big deal in the communication industry. And if you could send messages backwards in time, it would be a big deal everywhere. It would change our civilization in ways I have trouble imagining. But all of that is probably just an indication that the experiment probably won't work, because nature probably doesn't want to allow you to send messages backwards in time.
I don't really see retrocausality as a very plausible assumption. I mean, time clearly evolves or gets constructed towards the future. On the other side, I would also say that time is certainly a very poorly understood concept in physics or by physicists today, and one can certainly expect that in the future we'll have a much better and deeper understanding of time, and possibly a very different one from the one we have today.
So let's say that someday we develop that better understanding of time. After solving the riddle of quantum gravity, we build a working time machine. what would happen then? Would we be able to change the past? The answers are fantastic, disturbing, and a little strange.
Prehistoric Month starts Monday at 8:10 on Discovery HD Showcase.
We're trying to send signals back in time. And if that works, perhaps one day we can send humans back in time. An exciting idea, but it opens the door to the problem of paradox. A paradox is a situation that contradicts itself. Doesn't make any sense. Say you send a cure for cancer from the future to the past. Would the dead now be alive? See? Time travel is filled with such mysteries.
The things we would like to understand about time travel are, one, is it possible, even in principle, do the laws of physics permit backward time travel? We don't know the answer. We need the laws of quantum gravity in order to find out the answer. Second question is, if backward time travel is possible, then what does nature do about the so-called grandfather paradox? That I can go backward in time, then, if it's possible, and kill my grandfather before my father was conceived, thereby changing history so that I no longer exist. What does nature do about that?
The conservative interpretation is that space-time is one four-dimensional thing. It doesn't change. So if time travelers go to the past, they were always part of the past, and they don't change it. In other words, if you had time travelers aboard the Titanic, they might have warned the captain about the iceberg, but he didn't pay any attention to them, like he didn't pay any attention to the other iceberg warnings, because we know the ship ended up hitting an iceberg. So that's the conservative view, that time travelers don't alter the past. They can participate in the past. In fact, one wag once said that the real thing that sank the Titanic was the extra weight of all the stowaway time travelers on board to see it sink.
In fact, there is a simple reason we aren't surrounded by time-traveling tourists from the future. It's because no one has built a working time machine. Even if we someday have the technology to travel back in time, the machine will only work starting at the point we invented, creating the first loop in time.
When you create a time machine by moving cosmic strings up in the year 3000, you create a time loop up in the year 3000 by twisting space and time. So when the time traveler goes, he goes always toward the future, like this car. So he goes around the loop, and that means that he can go from the year 3002 back to the year 3001, but he can't but come back here to 2010 because that's before the time machine was built.
But there may be an exception to these rules. And, once again, it grows out of the weird world of quantum mechanics. Many quantum physicists believe there is an incalculable number of parallel universes, and these parallel universes are all around us.
Every time you make a decision that could have gone one way or the other, or you flip a coin, for example, it could have gone the other way, and then the universe would branch off into two separate branches in the many worlds theory of quantum mechanics.
If you allow for alternate universes, then lots of things can happen. It's still true that you have to avoid logical paradoxes. It's still true that what happened did happen, but it means that what happened in one universe happened in that universe. It doesn't apply to the new universe.
If the many worlds exist, which they do according to quantum mechanics, then what you would do is you go back to kill your grandfather. You kill a man who is identical to your grandfather, but he is only your grandfather in a parallel world. in that parallel world, your grandfather, being killed by you from another universe, is never going to give rise to your father, hence to you. But that's no problem, because you have never existed at all in this universe. What you've done in your time machine is cross the universes.
But there seems to be little chance of time traveling anytime soon, either into the existing past or a parallel universe.
The technology that would be required to make a time machine that has even a whisper of a hope of success is as far beyond us today as space travel is beyond the capabilities of an amoeba, because our technology is so puny. There's no hope at all.
Time travel seems unlikely if we approach it purely as a matter of taking a person or information from the present and transporting it to the past. But there is another way to journey into the past, a way that until recently would have been considered preposterous, but it's getting closer to reality every day. We could build the past. Human technology is evolving exponentially. When our computers get powerful enough, they could simulate massively complex worlds, including past eras of life on Earth. These wouldn't be video games. These simulations of the past would look and feel so real, you wouldn't know they are simulations. Not the genuine past, but the next best thing.
If you really want to go into the past, you're going to have to go into the extreme far future. In the extreme far future, they will have the ability to reproduce the past. And then you can see what the past was like. You can actually experience the distant past by existing in the virtual reality of the computers of the far future.